In the video 35 on the foundations of the computational economics course, now that we know how to numerically integrate functions, we will look at the stochastic consumption savings model, and we will be discretizing the choices as before. So just to recap, what are the components of a dynamic model? Remember, we have to have state variables that describe all of the relevant information for the decision maker to take into account, and these are the things that the policy function will be based on. We'll have to have decision variables, the vector variables that describe the choices, and the restrictions on the choice set that go along with that. Instantaneous payoffs, or the utility function that the decision maker is receiving, the utility that the decision maker is receiving in every time period. And finally, the motion rules, which describe the beliefs of the agents about the development of the states in the future, depending on the choices. And of course, we're looking for the value function and the policy function, which together constitute the solution of a model. So, as you would also remember, the Bellman equation, or the Bellman operator, completely defines the model. So once we're looking at the Bellman equation, then we can find all the parts of the model that we just went through in this one recursive expression. And then, of course, this recursive expression, which has function v, the value function on both sides, can also be thought of as an operator in the functional space, which takes as input some function v and produces an output, as an operator applied to that function. And so, since we should know immediately what the what the problem is described here, you should know. Let me give you 10 seconds to think about what problem that we are looking at here. And of course, this is the consumption savings problem. This is of course the cake eating problem. And how do we know that? Well, that's the transition rule for the cake, which is not eaten. We've seen this equation before. We've looked at the problem where the state is essentially describing the size of the cake available to the person at any particular time period, and the choice is how much of that cake to consume. With the instantaneous utility given by this U of C. Okay, so today we will go from the cake eating problem, which is an illustrative problem, to the consumption savings problem, which has several versions and appears in several different fields of economics, including micro and macroeconomics. So look at this Bellman equation. What has changed? Well, if you look and compare to the previous slide, it's not much actually. It's really just this transition rule that changed. It's more complicated now, but it's still based on m minus c. Oh, the notation changed, right? Then the state variable is now m, and there's only one state variable in this problem. The choice seems to be the same, also bounded from above and sort of bounded away. Or it must be non-negative rather. The utility function is of this variable c. So indeed, with a slight change, we can go from the cake eating problem to the consumption savings problem. And here the interpretation of the variables is like this. So m is now denoting the wealth of a person in the beginning of the period t, or in the beginning of any period, essentially. C is still consumption, but this is now unspecified what's being consumed. It's a consumption out of wealth, out of all of the resources that the decision maker has. No borrowing is allowed, and therefore consumption cannot exceed the amount of resources. There is still discounted factor beta and a time separable utility function, and we'll still we'll still take log for the utility. But now the new part is the gross return on savings and the income. And as you can see, they enter exactly here into the expression for the next period wealth. That's going to be whatever is not consumed grows with some growth factor R, and then there's income which is added on top of that. To convert it back to the Keynesian problem, of course, we would just set R equal to 1 and the income equal to 0. The interesting thing that we are introducing in this video, and from now on, I should say, is that both the return and the income can be stochastic. And the expectation in the Bellman equation cannot be dropped anymore, right? So we really have to add something here. And that's what we do, right? So now there will be an expectation of the future future value function, or the next period value function, that we have to calculate with respect to the uncertain income or uncertain return. Well, here we will focus on the income fluctuations, and for now we'll just fix the return. Okay. In principle, it's possible to have both being stochastic, but then we would have to calculate the two-dimensional quadrature, which I think is the next step. Today we will start with the one-dimensional stochasticity. Now let's assume that y tilde follows a log normal distribution, and let's set the location parameter to 0, and sigma, which describes the variance of this distribution. Let that to remain a parameter that we can change. Okay. So because this is a log normal distribution, then we are certain that the income will always be positive, and we also have the expression for the expectation of the income, which is sigma star over 2 under the exponent. So if sigma is really small, then income is fluctuating a little bit around 1. Okay, but let's also have in the code a special case to allow for y being exactly 0, with the purpose of being able to replicate the Keynesian problem with this new model. Okay, the solution method that we will use will be exactly the same as before, the value function iteration method. So as before, we would have to discretize the state space, assign some initial values to the value function defined on this state grid. And by the way, we can, in the discretized code, or discretized Keynesian code, we took the initial guess of the value function to be just the utility of the total resources, or the size of the cake. It could be 0 as well. It doesn't really matter where we start. And that's because we know that the Bellman operator is a construction mapping, and therefore it's globally convergent. So it doesn't matter where you start, you will always converge this Vfi method. So then we just need to code up the evaluation of the Bellman operator so that we can compute the next iteration approximation of the value function. And then while we're computing this next approximation, while we are applying the operator, then we will also record the optimal action, which will form the policy function. Right, and then we just do that over and over again until we converge. What's different? Well, now that we have the expectation inside of the Bellman equation and the Bellman operator, now we need to compute that expectation, and the expectation will be with respect to some random component in the model. How do we do that? Well, we just learned that in the previous video. We should do quadrature. Okay, so let's choose a particular Gaussian quadrature for that would be convenient to use. And my choice here was to take the Gauss-Lejeune quadrature, in part because it's a simply weighted one, closed interval, and let's see how it works. So this is the formula, just to remind you. And by the way, in the previous video in the slides, there was a typo that had to be corrected. It's going to be corrected in the repository. So here we are integrating on the finite interval some function, and that's going to be approximated with this first term, which is just the weighted sum of the function values in particular nodes with particular weights. Now, we will rely on this on the part of the NumPy package which produces the nodes and the weights for this quadrature. And so we don't have to worry about how that's calculated. And as you can see, the error term is really small with all these factorials in the denominator, although there's a fourth degree here. Well, anyway, the first term will serve as the approximation of the integral. Okay, so taking a sort of a little bit more detailed look at how exactly the expectation will be calculated. Here's the layout. So we need to calculate the expectation inside of the Bellman operator. We need to calculate the expectation with respect to the random income of the value function calculated in the points of the next period wealth, which is in turn a function of this random income. So we are calculating the expectation of some complicated function, some superposition of functions of this random variable. Okay, let's just use the definition of the expectation and write the integral between negative infinity and infinity. That's the function of interest. This is a PDF of the random variable. This is well, we assume that income is going to be a continuous random variable, so I'm applying the definition for continuous random variable expectation. The first step is to do the change of variables, where we introduce a new variable, which is by definition equals to the CDF of this random y, and then we can replace the we can do this the change of variable, according to the standard rules. And what we have is now we have an integral on the closed interval, and the PDF nicely disappears, right? And instead of y, we now have the inverse CDF of this new variable z. If the random variable y is continuous, then the inverse is well defined. And so we can go on to another change of variables now that we want to change the interval of integration such that it is between -1 and 1 and matches the quadrature. And this is easily done with a linear transformation next. And we have this expression, which is just another change of variable that can be, which now is almost like the definition of the integral, right? The function of interest is now this one. Everything else is exactly like we need for the Gauss-Legendre. And so it's approximately equals this weighted sum of the function, and this divided by 2 sort of pops out. And then we have the value function calculated at the next period resources for some particular points that are given by the inverse CDF, log normal in our case, of this linear transformation of the nodes of the quadrature. And then, of course, we can basically just pre-compute this part as we set up the quadrature, because the next period wealth will change, the value function will change during the Vfi Solver, but these points will be fixed. And so we can just, in the code, make a transition from the quadrature points and weights into this special quadrature points and special weights for our convenience. So we will be working with the class that we already had developed, cake discretized, and if you remember, it solved the deterministic cake eating problem by discretizing the choice space on the independent grid. So now we need to add the calculation of the expectation essentially to the Bellman equation. If you remember, the logic of the code that we already had written was that we were building up the maximand of the Bellman equation as a matrix. And so what I mean is that we were, in order to calculate this maximum, we would create a matrix that would contain everything under the maximization operator. And then, once that was complete, we could take the maximum along a particular axis. And so to make sure that we're taking maximum over the choices, we had choices in rows, and we would be taking maximum along the first axis, axis equals 0, so vertically. And we had states in columns, and the result would be relevant for each possible state in the state space. And thus we would have the vectorized version of the Bellman equation working. The additional things that we had to do was to mask off the infeasible choices and put minus infinity in there, so it would never be a maximum if the choice is infeasible. And then after this maximum along the axis equals 0 along the first axis, the resulting vector would represent the updated function for every point in the state space, right? So we've completed the calculation of this Bellman operator by taking the maximum along the rows, among the rows. All right, so to this machinery, we would like to add the calculation of the expectation. And the way we do it is we have to calculate this weighted sum of the value functions evaluated at different points. And this has to go inside, this whole thing, right? This whole thing has to go inside into the maximand. So now the logic will be more complicated, but similar. So now we want to calculate this part, the value function at possible tomorrow's next period's levels of resources as well, now the matrix is not enough, right? As a three-dimensional array. Okay, now bear with me. Then we will take the expectation by performing a matrix multiplication with the weights, and that would essentially result into the in the weighted sum. Then and the result would be a matrix. Then we would add the current utility to get, again as before, to get the matrix representing the maximand, and then we can take the maximum along the vertical axis. So that's the idea. Now you can see that we need an extra dimension for all the quadrature points that enter here, for all these different points where we want to calculate the value function, or the existing approximation of the value function that comes into the Bellman equation as an argument. And then once we calculate all these different values, which are now have to be for all possible states and choices, and all possible quadrature points, that's 3 dimensions. Then we want to multiply in a matrix way with a vector of weights. And that essentially would give us the linear combination of different values of v with the particular weights. And by taking the sum, we would reduce one of the dimensions again to get back to the matrix. So that's the idea. Okay, that's the idea of the code that we are looking at today. And here's the here's the plan, right? So we're building up the next period value function as a 3-dimensional array with choices along the first axis, indexed 0, states in axis 1, and this is what we had before. The axis 0 is the vertical one, and axis 1 is the horizontal one in the matrix. But now we will have a quadrature point dimension in axis 2. Once this 3-dimensional array is built, then we can use the dot product to multiply this 3-dimensional array with a vector of the quadrature weights, and we can check here. We can check here that it's actually possible to multiply the m by d array. No, we need this case here, right? If A, we're multiplying A and B. And you know, if these are just matrices, if both A and B are 2D arrays, that's the same thing as matrix multiplication with an @ sign. So numpy dot is generalization of the matrix arithmetics. So if A is an n by d array, and B is just a vector, or one-dimensional array, and this is an n-dimensional array, then the sum is a product over the last axes of A and B. Okay, so it's the last axis that the that the multiplication will work with. And let's just test it before we go into the Bellman operator code. And then once this multiplication is done, and so we obtain the weighted sum of the values at different possible incomes, so at different quadrature points, then we can add the current utility and then take the continue with our previous plan by taking the maximum among the rows. Okay, so here's a little code that I've written to test the multiplication of three-dimensional things. And here's again the NP dot. And we are taking this case where A is the n-dimensional array and B is a vector. That's the case that we're interested in. And so let's build A as a three-dimensional array. The first axis is going to have 3 elements. The second axis is going to have 4 elements. And the third axis is going to have 2 elements. Now, the way A is printed is not how I would do it, and I think it's a little bit counterintuitive, but this is the way that NumPy has it. You can see that the first axis with 3 elements is actually printed as layers, and then 4 elements on the second axis and 2 elements on the third axis. So, you know, I'm imagining a three-dimensional cube which is sliced along a particular axis, and then we're looking at these slices. Okay, what's important is that if we perform the dot product with B being the one-dimensional vector with 2 elements, then first of all, this product works because the 2 elements in the B's single dimension correspond to 2 elements in the last dimension of the A three-dimensional array. And you can see how it works, right? In the second dimension in A, it's all ones, and in the first layer is all zeros. So we should always get just the second number of the B's vector as a matrix, and that's what we actually get, right? And if I change it, the second one, that's what we get, and you know, the first element does not change, does not affect the result. So it's a little bit tricky, but with three-dimensional arrays, we can do similar linear algebra and matrix operations using NumPy. And vectorization, as you remember, is one of the ways to speed up the code. And so it proves to be a good approach in this problem. An alternative approach, just to mention, would be to either use a lower-level language or to use just-in-time compilation, which is provided by the number package in Python, to essentially produce a machine-level code that would run very fast and perform the loops really fast. But we don't touch it here. Here we are taking the vectorization route. All right, now once we are working with three-dimensional objects, then we have to make sure that we keep the dimensions in order. And it turns out that we will have to work with different inputs to the calculator of the next period wealth in different parts of the code. And it would be nice to be able to write it such that it works correctly with in different cases. And in particular, we need to solve the additional technical difficulty here, which is you know, converting scalars, vectors, and matrices into three-dimensional arrays. So let's see at this example of these operations that I'm doing here. Let's just start with this. A is a NumPy array made from a scalar, and I'm just printing here the shape and the number of dimensions of this object. You can see that A is 1. It doesn't matter, you know, which value is there. The important thing is that the number of dimensions is 0 when it's a scalar. There are no dimensions to this object, and the shape is just an empty tuple. If A is a vector, then we get the first dimension filled out, and the shape is a tuple of one element. So because there's only one dimension in the shape, whereas for matrices, you can see here is that once the A becomes a matrix, and the way I define it is just to, have a list of lists, so sort of a nested list converted to the NumPy array. Now there are two dimensions, x and y, and there are two elements in the first axis, three elements in the second axis. Finally, the things that we'll have to work with in this stochastic consumption savings model is the A of three dimensions, the array of three dimensions. And the way it's defined here in this example is just a list of lists of lists. So it's a double nested list of Python presented as a NumPy array. All right, and now we can see that there are three dimensions in dim. And in each dimension we have, 2, 2, and 3 elements in those dimensions. Okay, let me go back to the scalar here. And what I want to do now is I want to be able to convert every of these cases that A can be into a three-dimensional array. And here's a neat way to do it. I can try to change the shape. Let me start with a scalar again. So here we're changing the shape of the object A directly by changing its value, assigning it a different value. And this can be done, and it's guaranteed that Python will not change the location of the data that is stored in this array, which is good for the efficiency purposes. So there's no additional memory allocation or anything like that. It's just bookkeeping, essentially. But it's not always possible to do. It is in our case, because we're just adding new dimensions, essentially, which will be singular. All new dimensions should be singular, right? So one element in each of these new added dimensions. So here's how I do it. I'm just saying that shape should have some added dimensions. The plus equal, as you remember, is adding and then saving to the same variable. Adding in tuples means that we are adding new elements to the tuple. How many elements I want to add is calculated here. Multiplication for tuples is basically replicating or repeating the same tuple multiple times, same as lists. How many do I want to add? Well, I want the result to be three-dimensional, and the input has dimensions n dim. So I'm adding so many singular dimensions. And I'm writing this, I'm adding them to the shape that A already has. So this is what this line does, right? So it adds to the shape of A the dimensions with one element in each in the number of them that is needed to fill up the shape up to three elements. And then we can print that. And so here we are. If we start with a scalar, shape is nothing or empty tuple. There are none of the dimensions. The n dim is 0. After this operation here in line 9, what we have is we have still just one number, 349. But see, it's now in triple square brackets, showing us that this is the three-dimensional array. And indeed, there are three dimensions to it. But in each dimension, there's only one element. So the amount of data didn't really change. If we start from a vector of three elements in one dimension, then we can convert it into this representation, which has three elements in the first dimension, but then two additional ones are added. And now let's test it for a matrix. Same thing, we started with something and we ended up with three dimensions, 2, 3, 1 from 2, 3. So we added a singular dimension. And finally, if the input is three-dimensional, then nothing changes. Okay, so this is the second technical note that I wanted to make before actually going into the code. So here's the discretized k-ketene problem. from video 32, and this is here just for comparison. Let's run it so that we can invoke the code that is given here. But as you remember, this is a class which has the init method where all of the parameters are stored. And here we are defining the smallest positive number, and we're defining the grid for state space and the grid for choice space. And then oh yeah, there's an optimization flag there. Okay, and then the two essential part is the Bellman operator that takes an input of the value function here and produces the output as the updated value function, different values defined on the grid and the consumption. And then the solver, which implements the value function iteration solution method, right? Which is essentially a successive approximation solver for the fixed point of the Bellman operator. These are the essential parts. And let's now look at this new class called Deton for Deton's model. The main structure is going to be the same, but there are some differences. And let's go through this class part by part and talk about the essential details here. So the initialization method is pretty much the same. We also have economic parameters like beta and r, and now we have a new one which is sigma, right? Remember, this is the shape parameter, or the variability parameter from the log normal distribution of incomes. Then there is similar upper bound on the amount of wealth, the resources that defines the area of the area in the state space where we're solving the problem. We have the number of points for the state grid and the decision grid. So the way we are finding the optimal decision in this solution is the same as before. But now we have this additional number of points, which is the number of quadrature points that we will use for calculating the quadrature, the expectation of the next period value. And also here you can see that there is an interpolation method that is a parameter. And maybe let's start with that. We have a special method here in this class, which prepares the interpolation function depending on the interpolation method given in the class or object attributes. And you can see that it can be linear, quadratic, cubic, or polynomial. And this is the simple polynomial approximation. Now that we know many different approximation types, why don't we, code up the ability for this class to use different approximation schemes? As in the deterministic model, we will have to interpolate the value function, because we are discretizing choices separately from the states, and therefore we will have to calculate the value function that is input into the Bellman operator at different points between the grid points. Right. So this is the interpolation. I also wanted to say that this is the example now of this class Deton that could be developed into a sort of a well-developed, sophisticated class that would be useful maybe for your future research projects, or just on its own, right, and made into a module that can be used as a ready-made and tested code. And therefore, we're making less of shortcuts that we did before in the example codes. So in particular, having several different interpolation schemes is not a bad idea. Now, as you can see here, if you compare to the cake discretized class just above, in the init we're also setting up the state space and the choice space, so the grids are calculated right away. The problem with that is that in principle it is possible to create a model and then directly change the number of grid points in the model. And if that's done with the model cake discretized, then because it's only at the initialization of the object that this is performed, the generation of the grid. Then changing, say, the n grid later does not result in any changes in the grid that the object has internally. This is pretty bad. We shouldn't do it that way. Instead, we should do something that is done in this Deaton object, which takes some space, but it's fairly simple to understand what's going on. So let's think of this. Let's think of this n grid attribute, which is the number of grid points on the state space grid. It's set over here, all right? And n grid has some default value at the initialization, and we have an attribute of the class and all of the objects, of course, called n grid. Now, there is a special method, or actually a pair of methods here that have to do with n grid. So first of all, we are using this decorator to say that this method is actually a property, and what this does is that it defines this method as being the one that's called when we want to read from the property. So when we want to invoke the self n-grid, then this function here is run. And what it does, it just returns the value. Now the value is going to be stored, the value for the n-grid property is going to be stored into this double underscore n-grid, sort of the internal n-grid value. Then together with it goes this n-grid setter function. And this is a special function that is invoked every time we want to assign a value to this property, to this attribute. So in this line here, in line 17, we're assigning to the self n-grid some value. By default it's 50. When this line is performed, is called, then this function is actually called. And what happens is that first we with the input, which is n-grid. So first of all, we set the internal value for n-grid, which is double underscore n-grid. But then also here we can initialize the space of the state space. So the grid over the state space. So here we can invoke the NumPy linspace. Similarly to what we did in the initialization here, but now it's done in this special function, special method, which is the n-grid setter. And what we achieve is that every time n-grid is changing, then the grid of the state space will be recalculated because it's part of the procedure of changing the number of points of the state grid. You see? And the class then becomes more dynamic because now we can change the properties of this model on the fly and do not have to reinitialize the model altogether. And we can easily compare solutions that are produced on grids of different roughness, right, or different discretizations. The same goes for the grid over the choice space, and here the changes in nch grid are tracked, and every time nch grid is assigned, then the grid for the choices is recreated, is created over and over again. So let's see over here how it actually works. Look, let me first run only this one. So look here, I'm initializing the model with 2 grid points, and I'm just printing it out. Printout is trivial. It just lists a whole bunch of the properties of the class. And so here we have, here we have first Deaton model with 2 points on the state grid and 100 points on the choice grid, and so many quadrature points in the linear interpolation. And the state grid is this, right? This is what I'm printing here. State grid is this. But now we're changing the n-grid property of this object M, which is already initialized. And so in this line, we're just changing the number of grid points. and then we're printing the same information again. And the Deaton model now becomes the one with the same parameters, but with 3 points on the grid, and the grid on the state grid. And the state grid is now this one. It's recalculated, as you can see. So it used to have 2 points, now it has 3 points. It was from the smallest number to 10, right? So this is a scientific notation for 10. And now it has 3 points with 5 in the middle. And this is what coding the properties in this particular way allows you to achieve. Of course, now we have to work with quadrature. That's the whole point of this new development. And when the parameters that have to do with quadrature change, we also want to recalculate the quadrature weights, the weights that we saw in this expression here. So by quadrature weights and points or nodes, I'm going to call this Q star these guys, right? The Q prime and the W prime. What are the parameters that govern the these quadrature nodes and weights? Well, they are the parameters in the distribution of the income and also the number of these points. And so for these parameters, we have they're called sigma and then n quad being the number of points in the quadrature. And so we have 4 of these additional and special methods in the class that set or retrieve the values for sigma and n quad. And when the value of sigma and or n quad is set, either of them, then you can see here in line 61 and line 72, we're calling the internal function quadrature setup. Let's see what it does. So this is the internal function to set up quadrature points and weights. So essentially it just performs the transformations that we derived over here. So it has to do the inverse CDF of the log normal distribution calculated at this quadrature and weights and re-weight the weights. And that's exactly what happens in this procedure. You can see that we are calling the NumPy polynomial Legendre. So this is the function that returns standard nodes and weights for Gauss Legendre quadrature, and then we rescale to 0, 1, and then we apply the log norm PPF, which is the inverse of the CDF of the log normal distribution. And so you can see here that this is what we store in the self quadrature or quad P vector. They are already the Q's with a prime. And then we also rescale the weights by dividing them all by 2 and replacing the same values. Now here we're also performing only once what needs to be done with the weights. With the points. Namely, we are creating the 3-dimensional array in the same way we did it just a minute ago by changing the shape attribute of this array. And as you can see, we're creating the 3-dimensional array of these quadrature points where the first 2 dimensions are singular and all of the points are in the 3rd dimension. And this is going to be useful because we do want to treat the quadrature points as always being in the 3rd dimension. The first one being reserved for choices and the second one being reserved for the states. Now, there is this additional construction here with try and accept, and we didn't talk about that, I believe, in the course yet, but this is the way that Python allows you to manage the exceptions and errors. And so in this block of code, if the error is raised for some reason, then it is checked against this exception. And if the error is listed here, then nothing happens, right? We don't get the error message and the code is not stopped. This is the error that we allow. And we can do something if it actually occurs. In this case, we're not doing anything. So what is this for? See, this function, the quadrature setup, will be invoked either when sigma is set or the n quad is set, and one of these events will happen first before the other one had a chance to happen. And so it can be that the quadrature setup is called when the other part of this quadrature setup parameter, we set up sigma, and then n quad is not yet defined, and then this code cannot run because it needs both the self n quad over here and the self sigma over here. So we need both of these parts to be present. If they are not, then the attribute error is raised, and we catch it here, and we'll just wait. We just wait for the second parameter to be set. To be exact, I can see that sigma is set first, and then the n quad is set second. So when the sigma is set at the class initialization, then once this quadrature setup fails because the n quad is not set yet. But in the end, we get this quadrature setup working, and the quad p and quad w are saved as the attributes of the class, and we can work with this calculation of the expectations later on. Okay, so this is all I had to say about the initialization of the class. It's more complicated, but as you can see, it's more dynamic. And yes, since we did everything right, we can also change parameters of the quadrature on the fly. So we can initialize the model first with 2 quadrature points here, and then quadrature points and weights are here. And then, as I just say n quad equals 4, then the model is the same, except that now the quadrature setup is reinitialized because the n quad changed. As I said, this is very useful in economic modeling because you may want to have several models in a memory set up slightly differently, and you want to compare the outputs or the simulations. So, you want to compare the performance of the two models without reinitializing them over and over again. That was actually one of the common mistakes in the midterm work, where people would reinitialize the class when they needed to call the properties of the class for slightly different inputs. Okay, the rest of this class is the same as before. There is utility. Oh no, not quite actually. There is utility. We already looked at the function interpolation. Let's skip this. And then there is the Bellman operator and the Vfi Solver, so the successive approximation solver. There's an additional function that allows you to plot the solution, but we'll come to that later. So the Vfi Solver is pretty much the same. You can compare this solver to this solve here, and you'll see that it's doing more or less the same things. Well, maybe the callback is organized a little bit different. The biggest difference, of course, is in the Bellman equation, and I've tried to be very explicit with every line to explain what's going on here. But before going there, let's also look at this next period wealth function, which is convenient when you're working with models that are a little bit more complicated than cake eating problem, where the next period size of the cake is just the difference of the current size and the consumption level. So this calculates the next period wealth. And of course, the formula that we need here is written in the Bellman equation, and it's right here. We need to take the difference between the wealth in the current period and the consumption in the current period, multiply it with the gross return factor, and then add the stochastic income. Now we decided to fix R. And income is stochastic, so we calculate the expectation with respect to income. So that means, right? That means that we have to calculate this function as a function of income, where income is replaced by the quadrature points. So it's this part here that will be replaced with the quadrature points and lead to the three-dimensional array. Let's start with calculating the first part, which is simpler. So this is what's going on here. M1 is this what will be the next period wealth, and here it's without income. The gross return times the difference between the input of the current wealth and the current consumption. We want this to work in the vectorized mode, so both M and C could be scalars or vectors or maybe even matrices. Well, of course we will only call this next period wealth with the input arguments, with the arguments that make sense. This is kind of the internal workings of the model, and we don't necessarily have to check the inputs here, the arguments, because we are calling this function most of the time, at least. Okay, so this could be a matrix or an array. And as we just did a minute ago, we want to make sure that the shape of this M1 is actually a three-element tuple. So the M1 has to be the three-dimensional array already here. Okay, and then essentially in the standard case, we take this M1 as a three-dimensional array, and we add the quadrature points because we have to add the income, but instead of income, we add quadrature points, and they sit in the third dimension. So as a result, we return the three-dimensional array produced from the inputs that we'll already have, according to the Bellman operator design, states in columns and choices in rows. Now, there is a special case here, so I wanted to have a possibility to compare to the cake-eating problem, and therefore we have a special case, which could be done with an additional attribute of the whole class, but I thought that this way is also fine. So it's not very verbose, but we will only use it once, I think. So imagine that we don't want to calculate the expectation. We want to have just a deterministic problem as a special case of our problem, and we don't even want any deterministic version. We want a deterministic version without income, with income equal to 0. So we can check on the number of quadrature points, and if there's only one, then we just return the next period wealth without income. And therefore there's no plus component here. Okay, let's now turn our attention to the Bellman operator. As always, it has the input of the value function from the previous iteration of the successive approximation algorithm or other algorithms later on. What's this value function? Well, this is a one-dimensional array or one-dimensional vector of the values calculated on the state grid. So it's going to have the length the same as the state grid, namely n grid, the property, this one. And then we have to calculate the right-hand side of the Bellman equation. We already talked about the strategy, so we are creating the three-dimensional array with choices and states and quadrature points, and then doing some additional algebra. Okay, let's do that. So states is going to be the grid over the state space, and we want to put it into second dimension as a row vector, and therefore we are replacing the first, or we are creating the two-dimensional array with singular first axis and all the data in the second dimension. For choices, we're taking the choice grid, which is a separate grid in this discretized version, and we are placing all the data along the first dimension, so axis equals 0, but add the singular secondary dimension to it. Then this M will be states repeated along the first dimension for the number of times that is the number of points on the choice grid. So repeating the states, which is a row vector, along the first axis will create a matrix where the same row vector is repeated in all of the rows. And this is M. This is the current wealth state grid in columns. So it's repeated rows, and the numbers are the same in every column. And similarly for the choice space, we repeat the choices, which is the column vector, along the second dimension, which is axis 1, right? Indexing with base 0. And we do that for the number of times which is equal to the number of points in the state grid. And so this is the same sized matrix as M, but it has choices in rows. And so these are repeated columns. So every row has the same value compared to every column having the same value for M. Okay, now in principle, we could pass this to the next period wealth calculator. These two are matrices. On the axis, we would get a three-dimensional array with quadrature points added in the third dimension. But in addition, let's do this scaling of the choices similarly to what we called in the discretized cake class, the optimization of choice space, right? So this is a similar scaling that allows us to not waste points on the grid of choices that would be infeasible anyway. So we scale all of these choice points, or all of the points on the choice grid, every column, we scale with the corresponding point of the space, of the state space, which is the current wealth. And all of the choices have to be below current wealth because of the no borrowing constraint. This is essentially what's happening here. So we're taking the matrix and we're multiplying it element by element with this vector, and because of the broadcasting, then the vector is broadcasted in the right way. Okay, now M1, as returned by the next period wealth, is a three-dimensional array with quadrature points in the third dimension. These are the points where we want to calculate the value that the value function, which was the input to the Bellman operator. And therefore, we are creating the interpolation function. And here we're calling the self-interp func. And remember, this is the method. This is the method that looks at the attribute of the type of interpolation saved in the object and creates the interpolation function accordingly, using the axis and the points and the functional values as data. So this is what's happening here. We are passing the data of the state grid. This is where the value is always calculated, and the input value. This is where we are creating the interpolation function. And then we apply this interpolation function to the three-dimensional array M1. The result is, of course, a three-dimensional array V1. The interpolation function, keeps the shape of the input where the interpolation takes place. And so V1 is the three-dimensional object. And then, as we already tried, we perform a dot product of this three-dimensional array V1 with the vector of quadrature weights. This will result in a matrix, right, in a two-dimensional array with states in the columns and choices in the row, as we need. But now this represents the expected value function computed based on the V0 passed to the Bellman equation, or Bellman operator. Okay, we're nearly done. We need to complete the Bellman maximand now by adding the current utility calculated at C, and C is again the matrix. And then add to this the matrix EV, just discounted by beta, as we would have in the Bellman equation. And now this is completely ready for the final step. But just as a precaution, let's still do the filtering out of the infeasible choices. And the infeasible choices are given by the condition that C is greater than M. Both of them are matrices, and Mx is also a matrix. So we are indexing by logical expression here. And we put the minus infinity in all of the points of the Mx matrix where this holds. Finally, we can do the MPA max along x is 0. So now we're calculating the maximum on the right-hand side of the Bellman equation over this matrix Mx. And here, keep dims is false. So even though the maximum is calculated along the first dimension and produces a row vector, we don't want it to be a row vector. We just want it to be a one-dimensional vector. So it only has one dimension as opposed to a row vector which has two dimensions. And finally, still, we want to take all of the indices where this maximum was achieved by calling argmax. And then we want to index into the matrix C. C was a matrix, remember? We want to index using this argmax indices for the first dimension, and then range, which is just the list of all of the integers from 0 to up to the n-grid on the second dimension. So we are selecting from the matrix for each of the second index those which maximized in columns. And so these are the values of consumption that maximized the right-hand side of the Bellman equation. And this is what Bellman operator returns. So all in all, we have this nice vectorized Bellman operator which performs the expectation by doing the dot product, where the third dimension of the of this V1 matrix or a three-dimensional array is multiplied with the vector of quadrature weights. So this is where we are doing the quadrature calculation. And then Amax and argmax is, of course, where we're calculating the maximum in the right-hand side of the Bellman equation. Once we have the Bellman operator, then running the solver is as easy as always. We initialize the value function at some points, and here I'm using the utility function calculated at the points of the state grid as the initial value function, and then we just perform, as always, the successive approximations of these values by calling Bellman operator over and over again until we converge. There's a callback here as well. Now for plotting, what's happening is that essentially we're just calling the solver with a particular callback, where callback puts on the created in the beginning axis, it puts the current approximation of the value function and the policy function. And this illustrates the convergence of the successive approximator pretty well. Okay, we've looked at this. Let's see how the model performs. A couple of runs. You can see here that we are creating the Deaton model with a fairly small grid, 50 points in the state space and 10 points in the decision space. We first just solve it without doing anything, and then we solve it again while plotting the solution. And here are the plots. So this is the convergence that I've mentioned already. You can see that the initial one is probably here, and then as the successive approximations progress, then the value function, moves but converges. You can see how the distance between the functions uniformly becomes smaller and smaller. And then in red here, this is the solution to which we converged. The policy function is doing something funny. It has this wonderful jumps, this seesaw pattern. I mean, if you think enough, you would you will see that this it's not the staircase. Okay, why is it not the staircase? Well, that's for one particular normalization that we called optimization in the discretized version of the cake-eating problem, and it's right here. So if I just comment out one line here, then this should become staircase as before. And then the stairs are the discrete levels of consumption that we allow in the state grid. You can see how the value function changed shape completely. And well, of course, this is just a very small grid for the choice state. Therefore, we're getting this funny solution. But applying this normalization in the solver brings us to the situation where what's constant is not the level of consumption, it's the share of consumption. And therefore, we have this upward segments, which are probably not linear. Oh no, they must be linear, right? It's a fraction. So this linear segments in the policy function. And here's the second, in the second run, well, let's stay with the first run and try to make it look nicer. So the problem is the discretization of the choice space, of course. And if we discretize it more with more detail, then we get the function which is a lot less, jumping around. This is the standard, the default value for sigma, which would be nice to actually see. What's the sigma value there? It is 1. But let's look at the deterministic problem with income. And if we do that, this is the second run here. And let me just start with the deterministic problem. You can see what's going on. Compare this policy function. Remember, policy function tells you how much to consume for every possible size of wealth or amount of wealth. And here, it seems to have a very distinct kink. The policy function sort of, immediately converges in this part and then sort of takes some time to converge over here. But you can hypothesize that this is a linear function in the end, and all the jumping around is only because of the discretization and the inaccuracies in our solution. But this part is just exact, as it seems to be. And it is. It's a 45-degree line. Okay, and the question is, why do we get this 45-degree line in the optimal policy in the consumption savings problem? Should probably take a few seconds to think about that. Okay, well, the answer is that when there is no risk, so sigma is really small, as we set in this almost deterministic problem, there's almost no risk of deviating far from the expectation of the income in the next period. And remember, the expectation is the exponent of sigma square over 2, so it's approximately 1. With very little risk, you know that you will get an income of 1 in the next period. And that essentially means that if your wealth is below 1 now, you might as well consume it completely and then rely on the new income that you would get in the next period. This is the explanation for this very clear 45-degree section in the optimal policy, which tells you consume everything up to your probably discounted income in the next period, or maybe even not discounted. But this part here seems very close to what we had in the cake-eating problem, apart from this additional step. So let's do a comparison to the cake-eating problem, and hopefully we verify that this new code is producing a similar result to the cake-eating problem that we already solved. And this is a very good, probably the only good way to develop a computational model is to take a very simple example first, or a very simple specification, and then make it more and more complicated gradually, while always checking that the simplified special case still works. And so look at what we're doing here. That's also an example of having two models around in the same time. So M1 is going to be cake discretized with beta 0.9, 10 as an upper bound, and this discretization of states and choices. M2 is going to be Deaton's model with similar beta and upper bound, similar choices, and then I want to set the gross return to 1 to have no growing, no interest on the savings, essentially. And I want to set n quad to equal to 1. This is, as you remember, is a special case where there's no income. So the next period wealth, when the number of quadrature points is exactly 1, is just the wealth itself. So with r equal 1, we will just have m minus c as a cake eating problem. And so let me run this. And okay, what I'm doing then is I'm solving both of the problems, and then I'm plotting the solutions, the optimal policies, one on top of the other for cake eating and the Deatons. And as it appears, we're getting exactly the same result, which is a very good sign. So even though we're doing some quadrature and, three-dimensional arrays and all of that, the special case is still working, and the special case of the cake eating problem is still working here. Well, we can try to contrast the cake eating problem to the new consumption savings problem by trying to, or seeing how these solutions deviate. So for example, if I introduce some income, you can see immediately that, this is for sigma, which is fairly large. Let's make sigma really small. Okay, so we are seeing something which resembles this kink at around 1 over here. And then, a linear function here, it's almost linear over here. I guess I need to increase the number of grid points to make it even better. Yeah, the number of grid points over the states over the choice space. Yeah, something like that. So you can see that when you have income, it's optimal to consume more of the cake. Well, it's like you're getting a portion of the cake brought to you every day. It makes sense to consume more of the cake, whatever the size is, compared to the cake eating problem where you're just eating one single cake, which makes a lot of sense to me. So, it seems that we are able to solve this problem in a way that makes economic sense. And this, of course, is also a very important check for a numerical solution. Okay, there are several links here to CompEcon, and CompEcon is using a different solution method than ours to the similar problems or similar collection of problems. And so if you want to learn about the just-in-time compilation instead of vectorization in these problems, then it's definitely worth seeing. See you next time.